Light behaves as a wave, but how do we know that it is behaving as a wave? Well, one experiment that we can run is called the two-slit interference experiment. We take a light source and we shine it at a partition that has two slits that are about the same size as the wavelength. When the light comes through it, it acts as two unique light sources. And we get a pattern that shows light, dark, light, dark. This light, dark pattern comes from the fact that our light is interfering with itself. So if it is two wavelengths that overlap perfectly, where one has a crest and the other has a trough, they are going to add together and cancel each other out, giving us a dark space. If the light coming through those two slits, both of the crests and both of the troughs are lined up, we are going to get constructive interference, and that amplitude is going to increase. So we're going to get bright spots. Now, if it is acting as a wave, we would see a bright spot right between the two slits. And this is not something we would see if it's acting as a particle, because the slits would block our particles from showing up at that point. But because we have this constructive and destructive interference, we see this bright spot between the two slits. And because of that, we know that light is behaving as a wave. If we want to test and see if our light is behaving as a particle, we can do an experiment called the photoelectric effect. So we hook up a voltage source inside of an evacuated chamber and we irradiate a metal surface with light. If that light is at the correct frequency, it will hit an electron and make it jump off of the metal surface and be attracted to a positive terminal connected to a battery, and we can actually read the current that is produced from shining light onto this metal. Einstein explained the phenomena from the photoelectric effect as the fact that light had to have packets of energy with enough energy to emit that electron, to get that electron to jump off of the surface. And what he proposed was that it was made up of quanta, or also known as photons. So you may have already heard of photons. And so the energy of a photon is directly proportional to its frequency. So that light for the photoelectric effect had to have a correct frequency to have enough energy to get the electron to jump off the surface. This is inversely proportional to the wavelength. If we want to calculate the energy of that photon of light, we have two separate equations that we can use. Because it's directly proportional to the frequency, we can take h, which is Planck's constant. It's a constant of 6.626 times 10 to the negative 34 joule seconds, so joules times seconds, times our frequency in order to calculate the energy. And this is the energy of one photon. Okay. Alternatively, we have another equation that we can use if we're given the wavelength. So because we know that the speed of light is the frequency times the wavelength, if we rearrange this equation, we can plug it, let's rearrange it for frequency. We can plug this into the equation for energy. So if we plug it in here, we get Planck's constant times the speed of light over the wavelength, which is the second option we have for calculating the energy of a photon. So you can use this equation if you know the wavelength. You can use this equation if you know the frequency. So let's calculate the number of photons in a laser pulse with a wavelength of 337 nanometers. We know the total energy and we know the wavelength. So we're going to start by taking the wavelength and converting it into meters because it's given in nanometers. In order to use the speed of light, we need it to be in meters. So 1 nanometer is 1 times 10 to the negative 9th meters. So we get 3.37 times 10 to the negative 7th meters. Now we can find the energy of one photon. And here we have wavelength, so we're going to use the equation with wavelength. So Planck's constant times the speed of light over the wavelength. Planck's constant is a constant. Speed of light is a constant. And we just calculated the wavelength, so we can plug that into our equation as well. If we look at our units, the meters will cancel, the seconds will cancel. We'll be left with joules, which is what we expect for energy. So that is equal to 5.89 times 10 to the negative 19th joules. Well, we're not quite done. So that's the energy of one photon, but we're trying to figure out how many photons. So we're going to convert our millijoules to joules. So the total energy was given to us. And to calculate the number of photons, so the number of photons, that is equal to the total energy divided by the energy of each photon. So our total energy was 0.00383 joules. The energy of each photon is 5.89 times 10 to the negative 19 joules. And so we see that for this particular laser pulse, we have 6.49 times 10 to the 15th photons. So quite a few photons for even a very fairly low energy laser pulse. Here's a practice problem for you to try. See if you can find the frequency of the electromagnetic wave required to supply 100 joules of energy from 8.5 times 10 to the 27th photons. Pause the video and try to find the frequency. So to find the energy of the photon, we are going to have to take the total energy and divide by the number of photons. This will tell us how much energy each photon has. So if we do our calculation, we get 1.176 times 10 to the negative 26 joules of energy for each photon. Now that we know the energy of each photon, we can use the equation that includes frequency, which is h nu. So if we rearrange this to find frequency, we divide by h. So our frequency is equal to the energy of each photon, which we just calculated, divided by Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. Our joules will cancel and we'll end up with 1 over seconds. So our frequency is going to be 1.8 times 10 to the 7th hertz, or 1 over seconds.